I'm Sam Just. I work on RADOS as the PTL. I'd like to take today to talk in a little more detail than I think people usually talk to about sort of how recovery erasure coding in cache works. Hopefully this won't be too basic for you guys. So I'll be talking today about the RADOS. RGW, RBD, and Ceph are all simplified greatly by the fact that they all use LIBRADOS, or the object, or if you're more familiar with the code base, to talk to the RADOS cluster directly. RADOS is what handles replication, consistency, and data durability, so that RGW, RADOS GW, and Ceph don't have to worry about it. For Ceph, for example, the metadata and data are both stored as objects in RADOS. There is no separate storage. The MPS itself has no storage. So the RADOS interface tries to make it easy to reason about accessing distributed storage. Objects are divided into flat namespaces called pools. Each pool can have separate placement rules that allow you to place data on fast SSDs or slow hard drives, depending on the data, all within the same cluster. RADOS also offers strong consistency, which makes it a lot easier to reason about writing a system like RBD, since you don't have to worry about the possibility of an object going back in time simply because someone happened to reboot a server, which would be really annoying. RADOS clients are also able to talk directly to the cluster. That would be an RBD client or the RADOS GW gateway itself, or a Ceph client or the MDS. Thus avoiding a proxy layer and helping RADOS clients to get good parallels. Users can write applications for RADOS using the LIBRADOS interface available for all of the languages I mentioned before. The interface is quite rich, which poses some challenges for cache-carrying erasure coding, which we'll get into later. For one thing, we support partial overwrites of objects rather than requiring you to overwrite the entire object. This is nice for RBD, as you can imagine, because we can translate writes on the entire block device into writes on the individual 4 megabyte chunks fairly directly. Same with Ceph. It would be much more difficult if RBD needed to do a read, modify the 4 megabyte block in memory, and then write it back out. Each object can also have a set of user-defined metadata elements called XFs, pretty much exactly like you would imagine in a standard file system, but not necessarily stored in the file system itself. And RADOS also lets you define a set of key value mappings called the OMAP available on each object. This was introduced in order to support RADOS GW's bucket indexes, because it's difficult to do in-place updates of new S3 object names if you don't have access to some sort of ordered key value mapping. So every object actually has all three of these features. It's simply that not every application uses them. So every RBD block does in fact have an OMAP, it's just having data. And similarly, every bucket index has a data payload, it just doesn't have any data. Stop me at any time if you have questions, by the way. So I'll be quick here since I think everyone here is familiar with the Ceph cluster. But there are two basic pieces. We've got the OSD, which actually stores data. And then we have the monitor, a Paxos monitor cluster, which is essentially where the cluster gets its ground truth, if you will. All of the OSDs use information created and propagated by the monitors to make the same decision about data placement and migration. Though the monitors do not themselves actually orchestrate the data. Monitors are only involved in the data path insofar as a client needs to talk to the monitors before they can begin talking to the OSDs. But a particular object access does not require you to go through the monitor. So let's talk a little bit about Crush and how data is actually placed. So when a RADOS client tries to access the object, I've said that it is able to talk directly to the OSD that stores the object. But how does it know which object that is? One option would be to have some form of location service. Perhaps the client could talk to the monitors and ask them where to find the object. Or we could introduce another server. But we'd have to parallelize that, and it would be complicated. So it would be better if the RADOS client could simply know where to find the data. And the way it does that is by using an algorithm called crush. Crush takes a thing to be placed and a cluster map and outputs the location of the data. So, but instead of actually running the object name itself through crush, we instead hash the object name, map it to a placement group, and then run the placement group through crush. If you think about it, this is necessary because when you change the cluster map, you need to find out the new location of all of the objects. And it would be very slow if every OSD needed to rerun crush on every single object it was storing. There could be hundreds of millions of them. Instead, the OSD only needs to rerun crush on the 100 or so placement groups it stores. So there's a question that comes up a lot, why do we have placement groups in the first place? And this is the main reason. So crush outputs, in fact, an ordered set of OSDs. In this case, we are placing placement group 10 on those two OSDs. The first one it outputs will be the primary. So what happens when an OSD dies? Well, that's actually a cluster map change. The OSDs will report the failure to the monitors. Once enough OSDs have reported the failure, the monitors will publish a new cluster map marking this OSD down. This is exactly what you see when you run Ceph OSD dump and see an OSD marked as down. Because the OSD is marked down, Crush will skip that OSD and move on to the next one in the list, which in this case is this OSD. The old primary will then arrange for the data to be re-replicated to the new replica. It will eventually heal, the placement group will go active clean, and everything will be good. Note that, in that process, at no point did the monitors actually tell the OSDs where the placement group moved. The new primary worked that out on its own based on the new cluster map. So a nice property of Crush is that placement groups are declustered. That is, if two placement groups share a primary, typically their replicas won't. Or I'm sorry, if two placement groups share an OSD, typically the other replicas for those two placement groups will be on different OSDs. This means that if an OSD with about 100 placement groups dies, we won't have one new OSD performing recovery. We'll have 100 of them, each recovering about one placement group. So this drastically speeds up recovery and reduces hotspots due to recovery. Okay, so now we've got some basics on how data is placed. We can talk in a bit more detail about how RADOS handles failures and other changes to the cluster. So if placement is that dynamic, that is, if any minor change the monitors make to the placement to the cluster map might cause an arbitrary number of placement groups to remap, how is a primary for a placement group ever to be sure that it actually has the current version of an object? The answer is an algorithm called peering. You have probably seen this in your own clusters. If you cause a change to the cluster, a bunch of placement groups will go into a peering state and then eventually go active. And this is what they're doing in the meantime. Each OSD map generated by the monitors is assigned an increasing epoch number. The consistency of these numbers is guaranteed by the Paxos algorithm running on the monitors, so you never have to worry about there being two different maps with the same epoch number. The monitors will only ever publish one map with a particular epoch number, and they'll always be ordered. So the monitors and the OSDs remember all OSD maps back to the last epoch that all placement groups were clean. This means that every OSD is always able to walk backwards through time and figure out every OSD that has been responsible for a particular placement group back to the last time that placement group was fully recovered. And that is essentially the core of how peering figures out where to find rights it may not know about. So, to be really concrete about this, let's suppose that an epoch 20-220, OSD 11 is mapped as the primary for PG 1.4, with OSDs 5 and 30 as replicas. on its own, this mapping doesn't really help OSD 11 because as far as OSD 11 knows, it's brand new and it's missing tens of thousands of writes that it simply doesn't know about. Or maybe it actually is completely up to date along with its replicas and it can start serving reads immediately. So before it can serve any reads or writes, it must verify that the object it's serving a read on is current. So to do that, the primary walks backwards through its stored map and begins reconstructing the previous sets of OSDs. It finds that the acting set last changed in epoch 2113 before now, and 19884 before that. We were able to stop at epoch 19884 because OSD 11 has written down that it went active in that epoch. The so-called last epoch started member of the PG infrastructure, if you've looked through the code. It can stop there because if it went active in that epoch, it must have finished peering, and therefore the PG log it had at that time must already reflect all writes that happened before that. I'll go into a little more detail on that later. So in order to go active, therefore, OSD 11 simply needs to make sure that it hears from either OSD 5 or OSD 30, since any write completed in the epoch, in the interval where it was down, must be remembered by both of them, since any write must be completed by all replicas before being acted back to the client. We represent the state of the placement group on a particular OSD by keeping a list of the most recent operations on the placement group witnessed on that OSD called a PG log. Note, the PG log does not contain the actual data. It is not a data journal. It's just a list of modifications that have happened to objects. For each replica, if the replica's log overlaps with the authoritative log, that is, the log entries are numbered, so if the logs overlap, we can construct a complete list of every object that that replica is out of date on by simply walking forward in the list. If they don't overlap, we cannot determine which objects are out of date on that replica without scanning the PG story, a process known as backfill. So if we don't know which objects are invalid on the primary, we certainly can't serve reads. So if after peering the primary determines that it or any other peer requires backfill, it will request the monitor cluster publish a new map with healthy OSDs instead as the acting set. Once that map is published, peering will happen again, and the up-to-date peers will independently conclude that they should serve reads and writes while concurrently backfilling the correct peers. So suppose at epoch 1130, a placement group is mapped to 0, 1, and 2. Then the user does something crazy to the crush map. Maybe they removed a host or completely changed the crush parameters. I say that because this sort of thing wouldn't normally happen. Normally, one OSD might change. But if you were creative, you could get crushed to do this. And it remaps the placement group to OSDs 3, 4, and 5 instead. So OSD 3 will then go through peering. It will find that it has a completely empty PG log and no objects. But it will get a log from OSD 0 indicating that there have been hundreds of thousands of writes, and there are tens of thousands of objects. It simply doesn't have a copy of them. So it will find that it cannot actually serve any data since it has no objects. So it sends a message to the monitor requesting a temporary PG mapping. In fact, if you do a Ceph PG dump, you will see a list of all of the current Ceph PG mappings at the bottom of the output list. And it, of course, shows up in every OSD map. So if you dump an OSD map and then do OSD map tool print, you'll see them listed. So it sends this message to the monitor with requesting a temporary mapping of 0, 1, and 2, since those three OSDs are still perfectly capable of serving reads. So finally, the monitors produce a map with that mapping in epoch 1345. OSD 0 will peer. It will find that it is a temporary PG mapping, but that OSD 3 really can't serve reads. So it will conclude that the mapping is good. And it will begin serving reads and writes with 0, 1, and 2 as the acting set, while in the background, backfilling OSDs 3, 4, and 5. This state, where the current PG acting set is different from the current PG upset, that is crushed outputs, is known as a remapped, and you'll see this placement group in the Ceph-S mapping listed as remapped, and then remapped plus weight backfill, and then remapped plus backfill, once it gets around to actually doing the backfill. So once backfill finally completes, OSD0 will request that the temporary mapping be cleared. The monitors finally get around to doing that in EVICT 1391. OSD3 will peer, find that it's completely up to date, and then OSDs 3, 4, and 5 are good. OSD3 will then notify OSD0, 1, and 2 that they can delete their local copies of the PGs since the placement group has gone complete. So key to the backfill process is that we backfill in a well-defined object order. That is, all objects in Ceph are ordered by the H object order. If you're familiar with the code, you'll see that in common/hobject.h. It's the internal structure we use to designate an object. So we always backfill in H object order, and as we go, as we do backfill, the info.lastBackfill field will advance as we move further and farther through the PG. When we get a write on an object to the right of the backfill line, we don't send it to the backfill peer because that object hasn't been recovered yet. But if we get one to the left of the backfill line, we do send it to the peer, keeping it up to date. So we don't have to rescan after we've completed backfill. Everything will still be up to date because anything that changed, we will have sent to the backfill peer as well. So once backfill completes, everything is fully up to date, even if there were concurrent writes. And we only need to block writes for the brief period when we're actually recovering that exact object. So now that we've got a little background on how the peering and recovery stuff goes, let's move on to the new cache tiering features and how they fit into the overall Ceph design. Conceptually, there are two ways to think about how you could do tiering in a system like Ceph. You could either embed the tiering decisions in a layer under the OSD, for example, using flash cache or bcache or dm cache or any of those. And I think some people in the community have tried that. I'm not sure how well it's going. But the challenge is that you have to guess when you're doing your deployment exactly how much flash or fast storage to put in each node. And that can be challenging because you don't necessarily know the size of your working set. You don't know how much data you're ultimately going to want to store. So if instead we do our caching and tiering with different hardware for the cache and base tiers, we will be able to scale both tiers independently based on working set size and total data size. So our new cache tiering features address the latter approach. I mentioned before that pools can have different placement rules. This is important because the cache and the base tiers are themselves fully fledged RADOS pools with their own crush placement rules and their own replication rules and all of that stuff. So each tier, the cache and the base tier, are separately replicated, and it's important to note that they're both durable. So we can use write-back policies safely in the caching tier, and we can trust that the cache tier won't lose updates. So we can flush later. It's also important that the design allow the clients to understand the cache tier topology from the OSD map. So the cache tiering relationships are written into the OSD map along with the pools. So the clients are able to intelligently route requests to the cache or base tier based on the caching policy. That means that applications written on top of LIBRADOS don't care or need to know about. So RBD and RGW, for example, just work. You don't need to rewrite them to take advantage of cache tiering. So in write-back mode, a LIBRADOS client operating on the backing pool will read out of the OSD map that, in fact, there is a cache pool set up, and it will transparently redirect reads and writes to the cache pool instead. The cache pool is able to fully satisfy writes since it's set up as a write-back. On a miss, the primary for the cache pool instance of the object will delay the write while it promotes the object from the backing pool. But now recently, as of Infernalis, it's sort of unfortunate that in order to complete a 4 kilobyte write on a 4 megabyte RBD object, we need to promote a 4 megabyte RBD object before we can complete the write. Our friends at Intel have introduced a new feature that allows the primary to proxy the write back to the base tier. This is safe because the cache tier knows that the object isn't present, and so it's safe to do the write directly to the base tier. And we can still promote the object in the background after the proxy write is completed. So similarly with a read on a cache hit, we'll perform the read directly from the cache pool, which again is safe because the cache pool sees every write, and there's no possibility that the base tier has to do a copy. And similarly, in the event of a cache miss, the read can be redirected to the backing pool. Or in order to avoid a round trip, the primary also has the option of proxying the read to the backing pool. Possibly also triggering an object promotion based on the hotness of the object and the likelihood that it will be accessed again later. So we were able to make the cache tiering features fit nicely within the existing Ceph architecture because of all of the intelligence embedded at the RADOS client level. The promotion and eviction operations are themselves actually RADOS operations. The cache tier primary actually acts as a RADOS client to the base tier, and so the cache tier primary doesn't care whether there are failures or replication happening in the base tier. It does the same thing a LIBRADOS client does. It does those map updates and our resends requests as necessary. So,
can I ask a question?
Go ahead.
So this caching policy, where the software actually is running?
The part that actually makes the, you mean the part that makes the decisions about where to put it?
It will check the cache miss, cache hits, and...
It's in the primary itself, actually.
It's in the primary.
Yeah, so it's in line with the request template. The nice thing about the way it's structured is that there's no need for an external agent, since that would act as a bottleneck also. The primary for the cache tier version of the object is authoritative. It doesn't need anyone else's permission to work out whether it can promote or evict an object. So every OSD for the placement groups for which it is the primary makes all of these decisions independently.
So it means if you want an object in the SSD, but you have to visit the primary HDD OSD first.
No, it's the cache tier primary, which in this case would be the SSD primary.
Okay, so you visit the SSD OSD, and then decide you just get data from there, or you go to the...
Yeah, so currently it's a bit limited. It's either present in the cache tier or it's not. If it's present in the cache tier, then it's necessarily authoritative. It must be the newest copy. So if it's a read, the cache tier OSD will simply return the data. And if it's a write or there are other decisions to be made, that OSD is able to locally make that decision.
So you are saying it's either fully cache hit or fully cache miss. There's no partial.
For an object, yeah. And so there's been some discussion of that. My feeling is that that's a good design, and the reason is that RADOS objects are bounded in size. You're not allowed to have a multi-gigabyte RADOS object because it would mess up data distribution, for one thing. If you have 4 terabyte OSDs, you certainly can't have an object that's bigger than 4 terabytes, right? But if you have small objects, for example, RBDs are always broken into 4 megabyte objects, or bigger, it's configurable, but they're fixed size. Then those objects will be well distributed in the pool. So while it's true that you can't have a partial hit or a partial miss on a single object, you can have a partial hit or a partial miss on a whole RBD, because the RBD itself is broken into small RADOS objects. So it seems to me that if 4 megabytes is too big, then it probably would be solved by configuring RBD to use a smaller block size.
Okay. Is the eviction policy LIU?
It's based on the next slide.
Okay.
So the reason, just a little background, we're worried about using an LRU policy because you have to track a large list of recent accesses, and it turns reads into writes in a way that is distressing. So we're using blue filters instead.
Thank you.
So to make, as I'm sorry, I didn't get your name, but as you were, Sorry?
Ping, like ping pong, ping.
As Ping was alluding to, you need some way of estimating whether an object has been recently accessed to make intelligent decisions about whether to flush or evict the object, or code it for that matter. But you want to do this in a way that doesn't turn all reads into writes. So our current approach involves maintaining an in-memory bloom filter for a configurable amount of time, or until it reaches a configurable false positive probability. And then once the bloom filter fills up to that point, we write it out to disk. And we maintain the most recent end filters on disk, where end is determined by the user policy for how many hours of data they want to keep. And then we estimate temperature by walking back through the bloom filters we have stored and testing how many of them test positive for the object. It's not perfect. They're not counting bloom filters, so you don't know how many times an object was accessed in a particular time period. But you can get a good estimate of over how long a period the object was accessed. If it shows up in several bloom filters, then you know that it was accessed consistently over a long period of time. So this does let us estimate recency. We can certainly check the first bloom filter that shows up to get an idea of how recently it was accessed. And this informs our misbehavior, whether we promote or proxy the object. The policies are fairly simplistic at this stage. I think you can set it to simply promote if it's been accessed a certain number of times in the last hour, or a certain number of times in the stored hit sets, things like that. But there's nothing stopping us from making these policies much more intelligent based on the filters. So that would be a great place for further work if anyone has good proposals for other policies we could implement. Anyway, so in the background, I mentioned that the primary cache OSD is really in the driver's seat. It has authoritative information about what's going on for all of its stored objects. So in the background, every OSD is always scanning all of the cache tier PGs that it's primary for, and evaluating temperature, and then making decisions about whether to flush and whether to evict those objects. So of course, first you flush the object back out to the vacuum pool, which is actually a RADOS operation, and then we evict it by simply deleting it. So every PG has an internal tiering agent. There are configurable dirty ratios and full ratios, and there's a curve where as the placement group reaches its dirty ratio, it will start to flush hotter and hotter objects until it will flush any object, and same with eviction. As the PG fills up, it'll be willing to evict hotter and hotter objects until it's willing to evict anything, to make sure that that pool doesn't fill up. So as long as there's still space left in the pool, we make an effort to keep the hottest objects around, but as it fills up, we start to get less picky.
Question.
Go ahead.
So for your caching OSD, do you also have the same number of replica as you would have for your HTTP OSD?
No, it's completely independent. The base tier could even be erasure coded.
Okay.
It genuinely doesn't care. It's the same as it's a RADOS client to the backing tier, so it doesn't even know how many replicas that base tier has.
I'm thinking if you have write back, you need a replica, but if you have write through, you don't need. Do you agree?
So that comes up a lot. For a read-only pool where you always do write through, that's true. The challenge is that right now Ceph does pretty badly if you lose all of the replicas for a placement group. It's kind of designed not to lose data that way. That would be an interesting direction to explore, but the challenge isn't the cache during design. That's pretty easy. The challenge is making it so that Ceph is more tolerant of a pool where data loss is okay. So you would need to create a Ceph pool where the policy was that if there were no live replicas of the placement group, it just recreates the placement group MD and moves on with itself. Does that make sense? Yeah, so that would be another interesting project. But yeah, you're right. There is some ways. You have to replicate both at the cache tier and at the base tier. So if you're actually going to try to use cache tiering, there are some caveats. So everything I mentioned before suggests that there are round trips involved and writes involved in promoting, flushing, and evicting objects, and network traversals that are probably different from what you're used to with tiering systems. So the cache tier obviously needs to be quite a lot faster than the base tier for it. The cache tier also needs to be replicated, not least because we won't let you create cache tier on erasure code. Promote and flush are pretty expensive, so you need an object temperature that's really highly skewed. That is, most I/O goes to a very small number of hot objects, and they should fit within the cache. The cache needs to be big enough to basically, I said active sector, but I meant working session. The cache tier needs to be big enough to pretty much capture your working session. It's also pretty hard to benchmark. You need a realistic workload that actually reflects what your production workload will be, or you'll get either unnecessarily bad or unreasonably good results. And it takes a long time to warm up the cache. This isn't unique to Ceph's cache tiering, but just a thing to be aware of if you're trying to evaluate a setup. Okay, any questions about the cache tiering? I don't know if anyone else was completely unclear, or go ahead.
How can we enable the proxy read and write? My question is, how can we enable the proxy read and write?
How can you?
How can we enable the configuration of the proxy read and write?
I believe it actually does. So proxy. Someone more familiar. There are several people in this room more familiar with that code than I am.
I can answer you this question. And proxy read and write is enabled by default in the current main script code. Yeah. No, not Hammer. I think it's Kubernetes is enabled by default. But you need to set a parameter. The parameter is the mean read recency for promote or mean write recency for promote. You need to set these two parameters. Yeah. You can check the official document for the meaning of these two parameters.
Proxy read was enabled by default in
Kubernetes. Yeah.
Okay.
Yeah, I have the parent design. Similarly, the current design allows us to do the setup of different kind of test policy for the whole pro and the whole OSD, right? But compared with the high-end storage design, the current set statement allows us to set the different kind of test policy for the RBD side. I mean the unit of the RBD device.
I'm sorry?
Yeah, I mean the test policy can be set in unit of the RBD device.
Oh, so you're saying that if you have like RGW and RBD in the same cluster?
Yeah.
So if you have them in the same pool, they have to have the same cache array configurations. But typically people don't put RBD and RGW in the same pool. So you probably have two base pools and two caching pools, one set for each of RBD and RGW. And if you do that, then you can set the policies independently. So the policies are pool-wide, but you can create multiple pools.
So for RBD side, it doesn't support RBD side.
Sorry?
Currently, so I'm not sure I can you mean. So what do you mean that currently we cannot set the policy in unit of?
Oh, you mean on a per block device basis, for example? Is that what you mean?
For example, for the high-end design, we allow the customer to set up different policy, maybe the provision or maybe different kind of policy.
Yeah, if you have two RBD devices in the same pool, they will have the same policy. That's true.
Yeah.
So you would have to create multiple RBD pools with different policies and simply be clever about where you put the devices. But you're right, we don't have a more finely grained.
But I think the lot of time the customer need to set the maybe provision the provision the RBD device in the same pool.
That's interesting further work. The problem is that the OSD doesn't know about RBD block devices. How much time do I have, by the way?
Yeah,
Okay.
it's okay.
So very, very briefly, the RADOS doesn't actually know that there are block devices. So the challenge would be we need to create sort of directives that the RADOS client could send that mark the RADOS object with different policies. That would be an interesting direction. The other thing is that we would need to leave a redirect object in the cache pool. We probably want to do that for other reasons also. But yeah, at the moment, if you have two block devices in the same pool, they have the same policy.
We still need the next 10 minutes, so.
Okay, yeah. Okay, so let's talk about erasure. So before Firefly, Ceph, of course, only had replication, but 3x overhead to survive 2 OSDs of failure is kind of unfortunate. So with erasure coding, you can create 4 data chunks and 2 parity chunks and get 2 OSDs of failure tolerance for only a bargain 50%. So Ceph's approach to erasure coding requires the user to create an erasure coded pool with a specified erasure code, in this case, 4 data chunks and 2 parity chunks. That pool contains erasure coded placement groups. Each placement group, as with recovery, or as with replication, is assigned to an ordered set of OSDs output by Crush. The first 4, 1, 2, 3, and 4, get data chunks, and the last 2 get the parity chunks. Crush doesn't know or care that it's an erasure-coded pool, it just knows to output 6 replicas. Client requests, both reads and writes, as with replicated pools, go to the primary. The primary is responsible for doing the decode on reads and for parceling the write data out to the replicas. This costs us a network hop for reads, particularly, but it greatly simplified consistency because it lets the primary see reads and writes and do concurrency. So objects are striped across the data chunks, 1 to 4, with corresponding coding chunks stored in X and Y. Partial tail stripes include zero-filled data chunks as needed, if it just happens that the object isn't a multiple of the stripe size. More or less as usual. In order to read an object from an erasure-coded pool, the client computes the location of the object using Crush and sends a read request to the primary. The primary then determines which chunks it needs to read to fulfill the request. In this case, there aren't any failures, so we can simply read the 4 data chunks and then stick them together. The primary then reconstructs the object from the chunks it read and sends the reply back to the client. Same with a write. The client sends the write to the primary. The primary encodes the written buffer into updates for each individual OSD, sends them out. And then when it gets the replies from the erasure-coded replicas, it sends the acknowledgement back to the client. If we have a degraded pool, it works essentially the same way. We simply write to the OSDs we have. But suppose there's a brief power failure while the replicas are performing the writes such that replicas 1, 2, and 4 have completed the write, but 3, X, and Y have not. After the power comes back, we will go through peering exactly the same way as with the replicated pool as I described before. The primary will peer and find that 3 chunks have logs indicating that they are on version B, and 3 chunks have logs indicating that they are on version A. In fact, either version of the object is perfectly valid because the client did perform the write, but it didn't get an acknowledgement back. So either way we end up would be valid from a consistency point of view. With a replicated pool, we would simply choose one or the other. In fact, we would choose B since it's the newer version. And we would recover the other objects to version B. But with a replicated pool, we don't have 4 copies of either A or B. So we can't recover either one. So our power failure has actually cost us the whole object. That's not good. So there are some choices here. We can't simply write the data in place, as with a replicated pool, because it won't work for the reason I just mentioned. We could try complicatedly writing the data in place using some kind of a 2-phase commit or write-ahead log. But that would cost us a round trip and a second commit, and it still wouldn't be fast because these sorts of things you would be able to do would require a read, modify, write, which most people aren't willing to do anyway. So we instead restrict the interface to operations that we can roll back using local information without needing a data loop. Namely, we allow creates, appends, and removes, as well as xattr updates. Yeah, as well as xattr updates. For a create, we simply delete the object to roll it back, that's no problem. For an append, we truncate back to the old object size. For a remove, we never actually delete the object when we're doing the operation. We simply move it out of the way, and we write down what the name of the old object was. And then we clean it up once everyone's committed the operation. And then for xattr updates, we simply write down into the log entry or we simply write down the old version of the xattrs. So we stash this information in line with the log entry. So now, for an erasure coded pool, in addition to simply the name of the object, every log entry also includes a list of things you need to do to undo it. But there's still no data in the log entry, so it's still small, except for xattrs. For key value data, we simply don't let you do it on erasure coded pools because it's not. We actually couldn't figure out a way it would even be helpful or a good idea to put randomly updated key value data in an erasure coded pool anyway. So now, in the case of the partial failure we were talking about before, the primary will note that we have 3 versions at version A, and 3 versions at version B. And so we will simply roll back all of the ones at version B to version A, leaving us with a consistent placement. So the biggest thing that we don't allow is overwrites in the middle of an object. This means that you cannot run RBD unmodified on top of an erasure code. You can run a replicated pool as a cache tier on top of an erasure coded pool and run RBD. But and that might work once we get the cache ring performance up to a point where it's worthwhile. But other applications can consume erasure coded pools directly. RADOS GW, if anyone's familiar with the way it works, mostly writes out write once. It appends to the new data objects, and then only ever reads from them. It never overwrites those objects. So those objects can live directly on an erasure coded pool, so long as the bucket indexes are placed on a replicated pool, which makes sense. There are lots of systems that use replication for their metadata, and then erasure coding for the data. So there are actually a lot of ways to do erasure coding in terms of the actual math, breaking the object data into pieces. I didn't specify which one we use because we don't actually care. There is a pluggable interface for plugging in erasure coding algorithms. We've got a JErasure plugin, an ISAIL from Intel plugin, LRC, which layers over other algorithms. Each erasure code plugin simply needs to provide a few basic things like a way to encode and decode data, and a way to figure out which chunks you need to read in order to recover missing chunks. So briefly, in I think the 2 minutes I have left, erasure coding introduces one really awkward wrinkle in addition to what I've mentioned so far, and that's the cost of recovery. If you lose a 1 terabyte OSD of replicated DBs, you need to recover 1 terabyte of data from one place to another. Because of declustered placement, you're actually recovering like 1/100th of a terabyte on 100 different OSDs, but it's still 1 terabyte read and 1 terabyte written. For an erasure coded pool, though, with a 4+2 erasure code, you need to read 4 terabytes of data, and do a bunch of CPU and memory intensive operations to rebuild them. And that's where LRC comes in. LRC lets you layer an additional erasure code over one of the other plugins to let you create, in this case, rack local recovery chunks. So if you lose an OSD in a single rack, you can recover it using only the chunks in that rack. And a big thanks to all of the people involved. Right, so future work, lots of optimizations, making Ceph faster, SSDs, all of those sorts of things. I'll be quiet now so that if they don't